start. So the final block of today's session is Andrei Caldararu, who will speak about quantizing the normal number.
Well, thank you very much for the invitation to this great conference. I hope it will be a recurring event. And I'm afraid my talk will really go away from both models proposed by Mike Douglas. So it's going to be definition, theorem, no proof. But okay. So I want to start with, so this is joint work with Damien Kalak and my student Junwoo Tu, who's graduating this year. I want to begin with a very, very simple model for intersecting things. So the whole question will be about intersecting things. So let's start with Y, say, a smooth space. Now I'm going to build something that looks a little bit like a category. Let me call it C of Y, whose objects, so the objects are, let's say, smooth subvarieties X inside Y. And the morphisms between X1 and X2 are nothing but the intersection points of X1 and X2. Okay. Of course, this is a very, very simple model. How do morphisms compose? Well, this is the composition law is slightly strange in that it's composition over Y. But what this says is that if I look, I need to find a map from this to hom x1, x3. And I notice that this is nothing but x1 intersect x2, and then product over y with x2 intersect x3, which is obviously nothing but x1 intersect x2 intersect x3, which clearly includes into x1 intersect x3. Well, this is a very trivial model for how things intersect. And all I've done is put somehow a category version of this. Now, this example reminds very vaguely of the Fukaya category. Where the difference is that this Y is made to be symplectic, and these are supposed to be Lagrangian, and at least when things intersect transversely, you still get exactly somehow something related to the points of intersection, but made in a more complicated way into a complex using the Floer differential. Somehow, the way you should think about this is that this will get really complicated when the intersections are non-transversal. So I'm going to try to do something different, but also to deal with the non-transversalities. This will be the whole issue, that somehow when x1 and x2 are intersecting non-transversely and I don't just get a discrete set of points, things will become complicated. So let me also remind you there is another model of this, which is very closely related to this, which I think is called topological Fukaya category, which I have heard of in a talk of Cohen, but I'm not exactly sure who this is attributed to. So let's maybe call this C tilde of x, of y. The objects are the same, but now the morphisms between an x1 and an x2, they're just path inside y. So I is the unit interval, if you want, which start at x1 and end at x2. So the picture you should have in mind is you have some big space y, and you've got some x1 and some x2, and I've got so a morphism from x1 to x2 will be a path that goes from a point of x1 to a point of x2. So this is such an f. And it's obvious also how to compose three such things. If I have another one, which is maybe x3, and I have a g, sorry, another path g, which has the same starting and ending point. So g has the same starting point as the ending point of f. This y ensure this product over y ensures that tells me that I get a natural composition. I just stitch together paths. So this is all nice and fine. This is, from what I understand, how topologists are trying to understand the Fukaya category. You should also realize that you can restrict from this kind of model back to the original model by just saying, instead of all paths, I'm going to require constant path. Obviously, if I have to have a constant path which starts at x1 and then at x2, it must sit all the time at the point of intersection of x1 and x2. OK. So now I would like to maybe let me just say one more thing about this example, that in this example, now this hom from x1 to x2 can also be understood as this notion of homotopy fiber product of x1 and x2 over y. So maybe I'm not going to elaborate too much about what this homotopy fiber product is in the topological category. But the idea is that if you want to define a fiber product in homotopy theories, this is not well defined if you just take the ordinary fiber product. You need to replace one of your maps that by which you want to take the fiber product by a fibration. And this idea of taking paths is exactly the technology used in homotopy theory to replace a closed embedding by a fibration. OK. So now the goal of this talk is to do the same thing but in algebraic geometry. So the what will happen is that the ambient space Y will now be a smooth algebraic variety. And the X's will be smooth submanifolds. And somehow I could do the boring example of the intersection, and I wouldn't get anything particularly interesting. I would just get intersections as in the usual sense. But I could also try to do the this homotopy intersection. So now I would like to say that hom in my category between x1 and x2 is some kind of homotopy fiber product of x1 and x2, by which what I mean is the following. The usual intersection of two things, so if you really want to just intersect x1 and x2, if I want to understand, I mean, algebraic geometry, so to understand the variety, it's enough to understand the ring of functions on it. If I want to understand this ring of functions, that's the same thing as understanding this ring is the same thing as OX1 tensor product over OY with OX2. We all know very well that this operation is not left exact. So there's a left-derived functor of version of this. So if I want to get the derived intersection, I just take the derived tensor product here, which will just give me the structure sheaf of this thing. Okay? So now, morally, not just morally, what this really will be, you need to talk in the correct categorical context. This is no longer a sheaf of rings. It's a DG sheaf of rings. It's a complex of rings. So this thing is now a DG scheme. And there is, luckily for us, already a pretty well-developed theory of DG schemes. A nice model for this that will do almost everything that we need is due to Kapranov and Ionuț-Ciocan-Fontanin. Of course, the Toyen-Vezzosi and Lurie theories go much further, but this is the model that we will work in. Okay, and we see that there is indeed a composition. So the composition, just as before, should go from x1 fiber product over y with x2, cross over y, again in the derived sense, x2 cross x3 to x1 x3. And this at the level of sheaves of rings, that should go in the opposite direction, is just this map, OX1 tensor OX3. I'm going to stop writing all these R's and Y's. Tensor should map to OX1 tensor OX2 tensor OX2 tensor OX3. And there always is such a map. It's easy to show that there is a natural map. So our goal is to understand a few things. One is to understand these DG schemes themselves and these composition maps. So maybe let me discuss briefly why we care about this. So apart from a formal resemblance with topological with Fukaya category, so one particular application comes from the case when y is Calabi-Yau. Then these x's can be thought of as a D-brane in the topological, in the B model TFT. And then understanding this space of this home between x1 and x2 is nothing than the space of open string states. Well, I'm fudging here. You have to take some kind of global sections, but the space of open string states between x1 and x2. So if you have two branes, you want to understand the space of open string states between them in this B model TFT. This is almost word for word understanding this derived scheme. That's one application. A second application is the following. If I start with y, with any y, I can embed it as a diagonal inside y cross y. So now this is my old y, this is my new y. This is a little bit of a strange change of context, but understanding the open string states between y and itself inside y cross y, this has been argued maybe for 20 years already, that this corresponds to just studying the Hochschild homology. This is closely related to what David Ben-Zvi discussed. In fact, it's the so this hom YY is closely related to the Hochschild homology of the space Y. And maybe this is not particular, well, it is interesting, but not very much so. But more important is the fact that you need to understand these more, so you might say, okay, why do you need to understand the intersection of two things? Maybe you only need to understand the intersection of one thing, at least in this particular case. But if you're studying if Y is replaced by an orbifold, Y mod G, then you really need to understand these derived intersections, but between various, so home between various twisted diagonals, where these delta G and delta H are kind of the graphs of the actions. So delta G is the set of pairs Y G dot Y for Y in Y. Okay? There is a third example, which I'm going to really only mention in passing. There is some, the other reason you might want to study this is because there is this work of Kapustin, Rozansky, and Saulina, where they construct almost exactly this category. So they study this category, but for a target that is hyperkähler, for Y hyperkähler. And there are some physical implications that I'm not sure I fully understand, so I'm not going to try to say anything about that. But in that case, they only take for their axis the holomorphic Lagrangian submanifold. So it's some kind of a cross between the holomorphic and the symplectic story. All right. All right. So now let me try to tell you a few results. So what can we tell about this thing? So we have some general results for the intersection of two subvarieties, and then we have some very specialized results for when I try to intersect something with itself, which is kind of the most extreme case. So maybe let's begin by understanding this thing a little bit. So I'm going to first quote a theorem, an old theorem, which is in a paper of mine with Sheldon Katz and Eric Sharp, which says the following thing, that the cohomology sheaves of this complex OX1 derived tensor product OX2, these are all exterior powers of a fixed vector bundle E, where this E is the vector bundle on the ordinary intersection on x1 intersect x2, which is, well, let me maybe put here E dual. E is a vector bundle where E is just T y mod Tx1 plus Tx2. So this is the very first thing that you want to try to do when somebody gives you a DG scheme. You want to understand, first of all, on what topological space does it live. And that is usually given by its H. Well, in some naive sense, it lives on spec of H0. So in that case, it lives on X1, the ordinary intersection with X2. I will have some caveats about this in a minute. And then you want to understand what are the various other cohomology sheaves of this. And this theorem gives it to you completely. It tells you that they are exterior powers of this vector bundle. Now, if you look at this for a second, you will see exactly where all the interesting part comes in. So this is essentially interesting exactly when the intersection is non-transversal. In other words, transversality is exactly the statement that at each point of the intersection, the tangent bundles, the tangent spaces to the ambient subvarieties span the tangent space to the ambient variety. And if that doesn't happen, this is exactly when this vector bundle is non-trivial. And therefore, this DG scheme is an honest DG scheme, not just something, just the ordinary intersection. So from now on, I'm going to try to restrict my attention to the case, to the most extreme case of a non-transversal intersection. So from now on, I will look just at the case x1 equals to x2 equals to x. So in which case this vector bundle E is nothing but the normal bundle of x in y. So now the first important observation that you can do here is that all the calculation we want to do, they only care about the formal neighborhood of x in y. So when I'm trying to calculate this derived tensor product, if I were going to try to calculate sheaf x, this doesn't really care about what happens far away from x in y. It only cares about the formal neighborhood of x in y. And moreover, there is another very easy observation that all these calculations are easy. And really, when I say easy, I really mean easy. When instead of studying the formal neighborhood of x in y, when I look at the formal neighborhood of x inside its normal bundle. So if I just look at the 0 section in the normal bundle, computing this derived fiber product can be computed by just using a Koszul resolution. You get everything you ever wanted from it. So now the question is, how far is this formal neighborhood of x inside y from the formal neighborhood of x inside n? Or maybe rather than asking how far, I might ask, what kind of data do I need to distill out of the embedding of x inside y to be able to recover the formal neighborhood of x inside y from the data of x inside n? So this is somehow, if you want, a question, how far is complex geometry from just differential geometry? In differential geometry, the tubular neighborhood theorem tells us that these two things are exactly the same. There is always a tubular neighborhood of x inside y, which looks like the neighborhood of the 0 section in the normal bundle. In algebraic geometry, all we know is that this is a deformation. So x, y infinity is a deformation. of x n infinity. And you can see this by doing just a standard deformation to the normal cone. That gives you a flat family whose fibers look generically like x inside y. And at the special fiber, you get x inside n. You just take formal neighborhoods, you get exactly this. So now the question is, how do we keep track of this deformation? So I'm going to refer now to a very classic result, which has appeared both in physics and in mathematics. So let's look at a very particular case, which corresponds to the second case in here, the case of a diagonal embedding. So now let's look at how do x inside x cross x infinity, and then the normal bundle in this case is nothing but the tangent bundle. How do those two spaces differ? Obviously, in some sense, one of them is linear. This thing has got linear fibers. This one somehow, x, even around the diagonal, doesn't look linear. It's somehow curved. So the question is, how do we remember this curvature? And the answer to this was given in physics in this paper, which was already cited today once in the BCOV paper. This is in physics. In mathematics, it was given by a sequence of papers by Markarian, Kapranov, and with Kontsevich lurking in the background. And the answer is that there exists an L infinity structure on the space G, which is the tangent bundle of x shifted by -1 as an object of the derived category of x. So if you don't like L infinity, just think about it as a Lie algebra structure, which has also higher terms, but it's an honest Lie algebra. From which you can recover everything that you want. So this L infinity structure, this keeps track completely of this deformation. You can get, which can be obtained from a choice of Kähler metric. On X. So I have to emphasize that this L infinity structure is not unique. It's not completely determined by X. Its bracket, its lowest term is determined, but the higher terms depend on some choices. But the end result will not depend on, I mean, up to homotopy, this L infinity structure is not dependent on any choices. And then the main theorem, which was stated by Kapranov, says, completely characterizes both the formal neighborhood and the self-intersection. So maybe let me write this. If you take this L infinity algebra and take its Chevalier-Eilenberg complex, this gives exactly a resolution of the formal neighborhood of x inside x cross x. You need to do some completion here. And if you take the universal enveloping algebra of this L infinity algebra and dualize it, you get exactly the structure sheaf of this derived fiber product of x with itself inside as a diagonal. Okay? And moreover, this completely should answer both questions that we wanted. One is it gives a complete characterization of what the derived intersection of x with itself is. And you see that this thing also has a coproduct, which came from the product on your G. And that coproduct is exactly what gives you the composition of morphisms in the category that I started with. OK, let me and you get quite a few more things out of this. Maybe let me just mention that this had huge applications. This is the essential ingredient in defining Rosansky-Witten invariants without a Kähler metric. Without a hyperkähler metric. So the original definition of the Rosansky-Witten invariants was non-constructive, essentially, because you needed to have access to a hyperkähler metric, and nobody knows how to write such a thing. The point that Kapranov made was that all you needed to know were some cohomological invariants which can be computed. This was also used by Kontsevich to give his proof of the so-called theorem on complex manifolds, which says that the Hochschild cohomology ring of X is isomorphic to the polyvector field cohomology of X as rings. And this was used by Markarian and then by several other people to prove the Riemann-Roch. Myself, I also had a paper about this, to prove the Riemann-Roch, the formal Riemann-Roch theorem for Hochschild homology. So all of these come from this idea that this Tx minus 1 is a Lie algebra. Therefore, from this Lie algebra structure, you completely can understand this guy. Once you understand it, you can apply techniques from Lie theory to produce these results. OK. Now, what I want to tell you about in the remaining maybe 5 or 10 minutes is what results we have for the case of an arbitrary closed embedding. So that statement, everything that's up on that board, I've carefully put everything on one board. It only cares about the case of a diagonal embedding. So how about a general embedding? X inside Y. So you're asking, again, the same question. How does the formal neighborhood of X inside Y differ from the formal neighborhood of X inside the normal bundle? Well, you might think that there is a very similar answer, but it turns out that that situation is significantly simpler than the general case. So maybe let me just explain that there are two big differences between such an embedding X in Y and X inside the normal bundle. The two big differences are, first of all, when you look at X inside the normal bundle, there is a projection backwards. So this map, a priori, may not admit any map, even at the formal level, going back from Y to X, which kind of splits the inclusion. So this map might not look like a bundle even formally. So that's the first problem. So two problems. So maybe let me just say it like this. X to X infinity inside Y may not admit a splitting That's the first problem. And this problem was not visible at all in the case of the diagonal. There is always a splitting because you can just simply take one of the two projections, pi1 or pi2, and you get a splitting. The second problem is this nonlinearity, which was already apparent in the Kapranov picture. So it turns out that the correct context to address these two problems together is the language of Lie algebroids instead of Lie algebras. So the main difference will be the following, that the thing, so Lie algebra or L infinity algebra gets replaced by Lie algebroid. And maybe let me exemplify how this goes. First of all, on what space will we have? So up here, we had the fact that the tangent bundle shifted by -1 was nothing but the derived tangent space of the closed embedding of x inside x cross x. In general, when you have a closed embedding, the relative tangent bundle is 0 if you do it non-derived, but if you take the dual of the cotangent complex, if the two spaces are smooth, what you get is just a shift of the normal bundle. So the natural thing to say is that you will get a Lie algebroid on the relative tangent space of x inside y, which is quasi-isomorphic to n-1. Okay? And let me just give you as a flavor where, so a Lie algebroid comes with two things, a bracket, which I will, you should be able to see fairly soon that there is a bracket here, but it also needs to come with an anchor map. So the question is, where does the anchor map come from? So the anchor map in its very simplest incarnation should be a map from n-1 into Tx. Right? This is, for a Lie algebroid, you always get a bracket on this thing and an anchor map that goes into the derivations of the algebra that you care about. So what is this? This is nothing. So this is exactly the class of the extension. 0 goes to Tx, goes to Ty restricted to x, goes to n, goes to 0. So on whenever you have a subvariety, you have this short exact sequence, which itself gives you a class in x1 from n to Tx, which is nothing but a map from n-1 to Tx in the derived category, which is exactly what the anchor map is. Now, this is a huge oversimplification, because what happens is that everything has to be done at the infinity level, just as Kapranov also told us. And now, once this is an L infinity algebra, the anchor map is a map of L infinity algebras. A map of L infinity algebras consists of an infinite sequence of maps from tensor powers of this to that. So we'll need to construct more maps. This is just a first order approximation to what we're looking for. But you can see that already this thing is some kind of a obstruction to splitting. So this is exactly what addresses the first part of the problem. This is exactly the obstruction to splitting to first order, x into x1. So you might ask, OK, maybe this map is not split, but where does it stop being split? And this is a very classical question that even Grauert asked. And turns out that the obstruction to splitting the first order neighborhood is exactly the class of this extension. So now I can state our theorem. Maybe, but to keep the contrast with the theorem up there, I'm going to, with what's on that board, I'll use this thing, this board. So here's our theorem. There exists a DG Lie algebroid structure on the relative tangent bundle of x in y, which is quasi-isomorphic to n-1. Let's call this G. this thing completely recovers the formal neighborhood and the structure sheaf of the intersection. So the Chevalier-Allenberg complex of this G is exactly properly completed. Is the structure sheaf of the formal neighborhood of X inside Y, and the dual of the universal enveloping algebra of this Lie algebroid is the structure sheaf of X intersected with itself inside Y. And again, everything is properly functorial in the sense that also, for example, the composition map that I was discussing in the beginning for the composition maps for X intersected with itself 3 times are exactly what is encoded in this universal enveloping algebra of a Lie algebroid. And now maybe I will conclude with so as applications, you do get you naturally get Hochschild constant Rosenberg isomorphisms in some cases, which I'm not going to say exactly, but these give the generations of certain spectral sequences. For example, related to David Ben-Zvi's talk, the decomposition for the Hochschild homology of an orbifold is exactly obtained through techniques of this sort. And I would like to, before I forget. I will mention one more application in 30 seconds, and with that I will close. But before I do that, I want to mention also the work of Shilin Yu, who is here. He's a student at Penn State. So you might notice that here I've said DG Lie algebroid on this complex. This is a gigantic complex, which is extremely unwieldy to work with. You might want to do some kind of homotopy transfer of structure going from this big complex to just its cohomology. This seems easy, but it's not, because we are not working in the category of vector spaces. We're working in a more complicated category. So what Shilin did was he did the same thing that Kapranov did using a Kähler metric. And using a metric, he was able to actually construct a structure on this n-1, not on the relative tangent bundle, which is exactly an L-infinity algebroid, rather than a DG Lie algebroid on a much bigger space. So he produced an L-infinity algebroid on actually n-1 instead of a DG Lie algebroid on the relative tangent bundle. We probably have a technology to do the same, but I'm not yet entirely sure of the details. So I'm going to close with a conjecture, which I'm curious if this has any relevance to physics. The conjecture says the following thing. Again, X inside Y is both of them smooth. Then the center of the X algebra on Y of OX, OX is a deformation. It's something called the Poisson center of this very commutative ring, just all the cohomology of exterior powers of n. So this one is always a Poisson algebra. This we've proved. This is some non-commutative algebra, which is a deformation of this algebra. And we conjecture that the center of this algebra is isomorphic to the Poisson center of this Poisson algebra as rings, which is a generalization of Duflo's theorem and in representation theory and of Kontsevich's theorem on complex manifolds. So in physics language, this asks what open string states somehow commute with every other open string state as states between a fixed brane with both hands on the same fixed brane. I would be very interested if there is some physical meaning to this statement. Generally in physics, for example, for the diagonal embedding, this ring is already commutative, and this has trivial Poisson structure. And in the case of the diagonal embedding, this just says that the Hochschild cohomology ring of X is the polyvector field cohomology of X, which is Kontsevich's theorem, but which was always taken for granted in physics that the product on polyvector field agrees with the product in Hochschild cohomology, which is a priori not at all obvious. So I wonder if there is a physics argument that I have missed. Thank you very much.
Questions?
I sort of understand what the left-hand side is in physics, but I have no idea what the right-hand side is.
I'm not sure. Well, without the Poisson center, it's just this commutative algebra. You just take, if you want, the exterior parts of the normal bundle, sum them up, and take the del bar resolution and take the cohomology of that. The Poisson center it refers to the fact that there is a natural Poisson structure on this ring, and you're just taking all the things that commute with, for which the bracket is 0 in the Poisson structure. But all that I'm asking, is it clear that the center of this algebra can sit inside this algebra, can sit inside this algebra? This is a very kind of naive question. There is a conjecture of Duflo which suggests this should be true, but it's hard even in the context of the algebra.
Does your theorem tell us about the deformation theory of X and Y as governed by the quantity?
Yes. It says that you need to know that if you know, certainly if you know this V-algebroid, BGV algebraic structure or this L-infinity algebraic structure here, you know everything that you want to know about the embedded deformations of X and Y. They're completely controlled by this.
So does that mean that you would have like a Maury-Cartan equation with many higher terms?
Yes.
And would that be formal or is it actual deformations? Can you use this for actual deformations or only formal ones?
Certainly not more than formal. I mean, the question is if you. Yes, I think formal is the only answer. However, there is something that's strange in the literature, actually, now that you mention it. There are some papers, the author escapes me, where they claim that the only thing that we need to know to understand the deformations of X and Y are with the brackets in here, not also the anchor map. And it completely puzzles me why that claim is made. So I can't see how without knowing the anchor map you could understand the deformations of X and Y, but sorry, I don't know.
In general theory, why do you need Y to be smooth? I mean, in the beginning, maybe you need to intersection, but in this part, you really need Y to be smooth.
Okay, so the fact that X is smooth, neither X nor Y need to be smooth. For this part of the theorem and this part of the theorem, X and Y could be absolutely anything if you take this and instead of n minus 1, you just take the truly derived tangent, the relative tangent space, which could be some very complicated complex. For this theorem, actually, it's not true. maybe I should, this part of the theorem really for this one, what you require is that the tangent bundle of x in y is purely odd. So you see here, this is shifted by -1. It is purely odd. In general, what you would get here, you'd really get the structure sheaf of the formal neighborhood of x inside x cross x. So you get this even more more complicated thing. The essence of the proof of this thing is a statement that when you have something purely odd and you complete it in the symmetric algebra, you actually finish in finite time. The symmetric algebra of something purely odd is an exterior algebra. And so if you take the ideal generated by stuff in degree 1, some finite power of that will finish. So if you look at the case x over a point, for example, this is a statement that the differential operators are dual to the formal neighborhood of the diagonal, but that is not the full the formal neighborhood of the diagonal inside x cross x is not all of x cross x. Well, what I'm saying is that for odd kind of situations, this is the case.
Okay, let's